Hello everybody, my name is Jackie and today I'll do a presentation on the total synthesis of Aplysiasecosterol A. Before I begin, I just want to let you guys know that I have a hard time pronouncing some of these chemical compounds and names, so please ignore my French. So before I begin talking about the total synthesis of this compound, I want to talk about what steroids and what secosteroids are in general. Steroids are a biological compound that contain 4 rings of carbon atom linked in a specific configuration, as we can see in this picture right here. Steroids have very important biological functions, often serving as signaling molecules for activation of hormone receptors and altering cell membrane fluidity. Hormones are a target of study by many researchers because of their potent anti-inflammatory and immune modulating properties. Secosteroids are a subclass of steroids with a unique feature, a ring cleavage in the 4-ring framework, as we can see with the compound that we're going to study today on the top. Secosteroids are generally not explored much from both a chemical and biological perspective. Now, Aplysiasecosterol A is a 9,11 secosteroid isolated from a sea hare, Aplysias crudidae. It was initially isolated in 2015 by Kigoshi, Kita, and Kawamura, and it contains an extremely unique tricyclic Y-diketone core attached to a densely packed cyclopentane with large substituents. The group also found 2 congeners, compounds that are related by origin, structure, or functions, Aplysiasecosterol B and C, and we can see that in this picture right here. They're different by the R groups, and the R groups are labeled right here. Unfortunately, the biology of Aplysiasecosterol A is not well known due to the scarcity of the compound. However, in 2016, Sung, Xu, and Wu's team isolated Penigorgios A, B, D, and E from the Gorgian Penigorgia species that contained the Aplysiasecosterol A skeleton. As we can see with this picture right here, the skeleton resembles a lot like the Aplysiasecosterol A skeleton. Specifically, the Penigorgios A was found to have the ability to induce apoptosis of hepatic stellate cells, which are just fat-storing liver cells. So that was very interesting, and the team saw the challenge with this compound and therefore reported the first and asymmetric total synthesis of Aplysiasecosterol A. Now, the complete synthesis of Aplysiasecosterol A is divided into 3 parts: the left-hand segment, the right-hand segment, and the combination of both segments. The left-hand segment refers to the tricyclic compound that we see here, and the right-hand segment refers to the cyclopentane compound. Since the total reaction for all 3 parts add up to over 30 plus reactions, I'll just be talking about a couple of the very interesting steps that we have covered in organic chemistry and a lot of the other mechanisms that we have not seen yet. So let's talk about the retrosynthetic analysis for this compound. The complication arises from the construction of the C ring, which we can see in this red ring right here, and in the D ring, which is the cyclopentane ring right here. The structure and the position of the C ring is placed in which the pentane is bent upwards, right here. The stereochemistry of carbon 10, which is right here, which also has to be taken into consideration because it's also in a position where it's bent upward. So this carbon 10 contains 4 substituents attached to it, and also the configuration of carbon 6 and 7 also had to be considered. So the team decided on a desymmetrization strategy. To address the D-ring problem, the team considered a disconnection at carbon 13 and 14, which is right here. To deal with the stereocenter of carbon 13, 14, and carbon 8, the team decided that a hydrofunctionalization of unactivated alkenes via metal-mediated hydrogen atom transfer was a method for the construction of the stereocenter through an HAT-based alkene cyclization reaction. I'll talk more about that reaction towards the end. This method gave the compound 8 as an intermediate, and that can be made from compound 9 and 10 through a Reformatsky type reaction. The group cleaved carbon 5 and 7 of the compound 9 to found a cyclization reaction, and further simplified of compound 9, and we get a diketone product that we can purchase and that we can get very easily. And then compound 10 looked like it arises from plus citronol, which is compound 14 right here. So this is the overall synthesis of the left-hand segment. See, the most difficult part about the left-hand segment is the formation of the tricyclic compound. For this segment, I'll direct my focus on how they achieve the step. Specifically, I'll talk about from compound 22 right here to compound 11 and compound 11 to compound 23. This is the reaction of the TMS eno ether formation. The carbonyl oxygen acts as a nucleophile and attacks the TMSO-TF group because sulfur in the compound is highly electrophilic. This reaction kicks out CF3 as a leaving group. Triethylamine acts as a strong base and deprotonates an alpha hydrogen to create an eno-like structure. This is the intermediate. Now this is the IBX oxidation, and IBX stands for the O-iodoxy benzoic acid to form an alpha-beta unsaturated enon. This reaction is catalytic, in which the catalyst is the MBO compound. So this is the reaction between the MBO and IBX, the MBO, which is this compound on the left, and IBX is the compound on the right. The negatively charged oxygen attacks the electrophilic iodine, making it more electrophilic in the process, and I'll tell you more and the reason for that in the next slide. So the reason for this attack is to activate the iodine compound, to allow the enon to attack the iodine compound. The enon acts a nucleophile and attack the electrophilic iodine, kicking out the OH as a leaving group. The OH acts as a nucleophile and attack the electrophilic sulfur, kicking the electrons back to the oxygen to restore charges and expel out the sulfur as a leaving group. The negatively charged oxygen on the IBX compound acts as a base and deprotonates a beta hydrogen, which is right here, forming a pi bond between the alpha and the beta position and kicking out the iodide compound as a leaving group and producing the alpha-beta unsaturated enon. Later on, this molecule of the IBX and MBO group is regenerated to reproduce the catalyst. Now this reaction here is a kind of a special reaction. It contains a radical initiator, which is the V40. It's a 1,1-azobis cyclohexane carbonitro and this silicon group here. This reaction undergoes a radical reaction. Interesting. So first, this is the radical initiator with the V40. This process creates N2 gas, which bubbles out of the solution and drives the equilibrium forward, so we're producing a lot of radicals. So here is just a standard radical hydrogen abstraction. This radical here from this compound that we produced earlier is going to abstract the hydrogen from the silicon group, forming this silicon radical here. Now this silicon radical here will do a pi bond addition to add to the less substituted and create a tertiary radical. Now this tertiary radical will do another pi bond addition here and add to the beta position, forming a radical in the alpha position. Now the alpha position will undergo a radical hydrogen abstraction here to add a hydrogen to the alpha position. Now there can be a radical halogen abstraction. This bromine will be abstracted to form a tertiary radical in the beta position here. Now this radical here will just do another hydrogen abstraction to add the hydrogen in that tertiary position. And here is another hydrogen abstraction, this time in this tertiary carbon here, to produce a radical in this tertiary carbon. Now this is a radical elimination here, where this radical here will form a pi bond between this carbon and kicking out the silicon group as a leaving group, producing a radical. And obviously the radical will end through coupling between two radicals. So this is the overall synthesis of the right-hand segment. There are a lot of very cool reactions in this synthesis, but I believe the most interesting part is from compound 28, which is right here, to compound 30. Compound 30 was a direct backbone that contained a carbonyl that allowed an alpha proton to get deprotonated that created the large substituents. Later, the amide underwent a series of reaction, a methyllithium addition here, a hydrazone formation, an iodination, to create compound 34, which just underwent a Suzuki coupling to get compound 36 and underwent oxidation to install the aldehyde here. So those mechanisms and those reactions, we have seen those before. So I want to direct my focus on compound 28 to 30, which is right here. So as you can see, this synthesis took 3 steps: a Des-Martin, a Pinnick oxidation, and a condensation. So this is the Des-Martin oxidation. We have seen this many times in organic chemistry. It converts a primary alcohol into an aldehyde. And here's the Pinnick oxidation, where the aldehyde is converted into a carboxylic acid. And we also have seen this in organic chemistry, so I'm not going to go over this. But I did do a step-by-step mechanism of this, so I won't explain it, but you guys can pause the video to see it if you guys want to. So here we're doing a condensation reaction. So this compound right here is condensed with plus 1R, 2R pseudoepenamine, which is just this compound, with pivenyl chloride and triethylamine. The triethylamine acts as a strong base and non-nucleophilic to deprotonate this carboxylic acid to form a carboxylate salt. Now this carboxylic salt acts as a nucleophile and attacks the pivenyl chloride, which is very reactive because this is a carboxylic acid derivative. This is the most reactive one, to form a tetrahedral intermediate. Now the lone pairs on the negatively charged oxygen kicks down to form the strong carbon-oxygen double bond and kicking out the chlorine as a leaving group and creating an acid anhydride. Now this acid anhydride is now reactive enough to be attacked by a nucleophilic amide. The lone pair on the negatively charged oxygen kicks down to form the strong carbon-oxygen double bond again and kicks out the carboxylate as a leaving group. The carboxylate now acts as a base and deprotonate the hydrogen from the amide to generate our product. So this is the complete synthesis of Aplysiasecosterol A. The most interesting part about this synthesis is the first 3 steps. The first step underwent a Reform-Maskey type reaction, and the second step is the dehydration reaction, and the third step is the hat radical cyclization reaction. So I will direct my focus on the last 2 steps, which is the dehydration reaction and the hat radical cyclization. So under these conditions, the Utimoto conditions, which is just these compounds here, these reagents, we just afford an anti-aldo product. And this undergoes a Reform-Maskey type reaction, and we have seen these reactions, just the reagents a little bit more different. But we installed an OH in this position here. Now this is the dehydration of the beta hydroxy ketone with Burgess reagent, and the Burgess reagent is down here. I wrote it out for you guys in case you guys want to see what I'm saying. It's a methoxy carbonyl sulfomoly triethyl ammonium hydroxide, and is a mild dehydrating agent. This reagent can also oxidize primary and secondary alcohol to give their corresponding aldehyde and ketones a very good yield. So the mechanism for this is that the oxygen, the OH, acts as a nucleophile and attack the electrophilic center of sulfur, kicking out the triethylamine as a leaving group. The nitrogen with the negatively charged does an elimination by deprotonating this hydrogen here and forming a double bond here and kicking out this giant compound here to create an E configuration of the double bond. So ignore all the messy arrow here. I tried fixing it, but it was just really hard and the program was kind of weird. So this reaction is the hat radical cyclization reaction to produce our desired product. The iron dipivenyl methanate acts as a source of radical initiator and a catalyst to create a radical. And that radical will react with isopropoxyphenylsilene, which is this compound here, to generate a hydrogen radical. So basically this whole reaction here will just generate a hydrogen radical, hence the name, a hydrogen atom transfer. The hydrogen radical will do a pi bond addition to add the hydrogen to the less substituted carbon and generate a tertiary radical here. Now, the tertiary radical will do another pi bond addition to form a cyclopentane compound to form another tertiary radical. The reason for this stereochemistry here is because once the radical does an addition to the pi bond, since the carbon is already going into the page, it will continue to retain the stereochemistry after the addition because it's going to do an addition at the backside, forcing the methyl to go out of the page. The tertiary radical will react with another hydrogen radical to form our desired product of Aplysiasecosterol A. So here's some of the key innovation conclusion here. The combination of 1,1-azobis cyclohexene carbonyl nitro and the silicon allow for the formation of the tricyclic compound in the left-hand segment. Compound 28 underwent two oxidation, Desmartin and a picnic, and a condensation to form a general skeleton backbone of the right-hand segment. A reformed Massey type reaction allowed for the combination of both segments, and a dehydration of the beta hydroxyketone allowed for the insulation of an E configuration stereochemistry. The final compound was created by the hat radical cyclization with very good yield. Here are my references, and that concludes my presentation. Thank you so much for listening in. I'll catch you guys later.